Welcome to Lecture 1 of CHEE 1000. You'll notice that in the lower right-hand corner or along the bottom, in red will be the text for the narration. The agenda for this lecture is provided here. We'll cover the basics of performing engineering calculations. If asked how far is it to the store, would you respond 5? If asked how much time is left in class, would you respond 5? If asked what is the mass of sugar required for the cake, would you respond 5? If asked how hot is it outside, would you respond 5? To answer these questions, something else is needed in addition to the number. To specify an engineering quantity, both a value and a unit must be provided. Examples of this for the questions asked in the previous slide are given here. For example, 5 yards is a meaningful response to the question, how far is it? A unit is a specific value of a dimension, which in turn is a measurable thing. Length is one such dimension, for which a unit can be defined. Many other dimensions exist. A system of units is a group of values specified for each dimension. The two most common systems are SI, System International, and the American Engineering System, AES. SI is used internationally, while AES is used primarily in the US. This table provides values of base units for 3 dimensions. These base units can be used to define multiple and derived units, as described next. Multiple units are multiples of the base units. In the SI system, these are defined as multiples of 10, except for time, while in the AES system, these usually are not multiples of 10. In the SI system, the multiple of 10 commonly is specified by a prefix, such as kilo, which indicates a multiplicative factor of 10 to the power 3 or 1,000. Other prefixes are provided on the slide. You should memorize these. Derived units are units representing physical quantities that are given by multiplying and/or dividing base units. For example, force is defined as a product of mass and acceleration. Acceleration is defined as the rate of change of velocity, units of meters per second squared. Thus, the units of force are equal to the product of mass and acceleration units. The units are kilograms, meters per second squared. The Newton, denoted by N, is defined to be a unit of force equal to 1 kilogram meter per second squared. Its use simplifies specifying force quantities. Note Pascal is a derived pressure unit equal to 1 Newton per square meter. Derived units for energy and power are presented here. Note that energy and work have the same units. Also note the definitions of joule and watt in the SI system. Engineering calculations require multiplying, dividing, adding, and subtracting quantities. These calculations involve both the value and unit of the quantity. When multiplying or dividing, the values are multiplied or divided to obtain the value of the calculation. The units also are multiplied or divided to obtain the unit of the calculation. However, quantities can be added or subtracted only if they have the same unit. For example, one cannot add 10 meters to 5 yards without first changing the units of the two quantities to a common unit. Meters could be converted to yards, or vice versa. Unit conversion often is required to add or subtract quantities. An approach to performing these conversions is presented here that helps to eliminate mistakes. The process involves 3 steps. First, identify the desired unit. Second, look up a conversion factor. You may need more than one. And third, perform the calculation. A conversion factor is a ratio of 2 quantities that are equal, as illustrated on this slide. Note the use of scientific notation to represent values that are multiplied by powers of 10. You probably have used the E notation on your calculator or computer. 2 ways to find the quality needed for a conversion factor are to use the table provided here from Felder and Rousseau's book, or use Google to search for it. Try the 2 example searches to see how easy it is. Suppose you wish to change the units of the quantity 0.2 kilograms to pounds mass. Note that pound, lb, can represent a mass or force. The subscript m denotes this unit as pound mass to differentiate it from pound force, lb sub f. The conversion process starts with putting the desired unit to the left of the equal sign above and creating a grid on the right of the equal. The grid has 2 rows and multiple columns, depending on the conversion performed. The quantity for which the units are to be converted is placed in the upper row of the first column. 2 equalities that can be used to create the desired conversion factor are provided here. You can find these equalities using Google or the table provided previously. The quantity on one side of the equality will be placed in the top row or numerator of the second column, and the quantity on the other side in the bottom row or denominator. The quantity with the desired unit is placed in the numerator, and the quantity with the undesired unit in the denominator. The first equality is used to create the conversion factor in the second column by placing the quantity with the desired unit in the numerator and the quantity with the undesired unit in the denominator. The other equality could be used instead and would give the same result. To perform the conversion, multiply the values in the numerator of the grid and divide by the values in the denominator. This gives a value of 0.441. Likewise, multiply the units in the numerator and divide by the units in the denominator. The kilogram units cancel, leaving the desired unit of pound mass, and the conversion is complete. Alternatively, you can ask Google to perform the conversion as shown. To perform the conversion here, 2 conversion factors are needed, so 2 columns have been added to the grid. You do not need to determine how many conversion factors are needed, as you can always add more later. The factors are to convert pounds mass to grams and feet to centimeters. The first conversion factor is convert the mass unit of pounds mass to grams. We can verify the desired unit is obtained by canceling the pounds mass unit. The second conversion factor is to convert feet to centimeters. Multiplying and dividing the values in units yields the quantity with the desired units. Google also can be used. Newton's second law of motion leads to the definition of force in base units of length, mass, and time. However, derived units also are used as discussed previously. The equality of quantities of different units is provided here. These equalities can be used to create force conversion factors. Force conversion factors are often denoted by the symbol G sub C. We can use the grid to guide calculations as well as perform unit conversions. Suppose you are asked to calculate the weight, or force, of a 10 kilogram object on the moon, where the acceleration due to gravity, g, is 1.6 meters per second squared. The result is to have a unit of Newton. To perform this calculation requires use of Newton's second law. Weight is equal to mass times acceleration due to gravity, and a force conversion factor. The calculation of the weight from Newton's second law is shown. The required conversion factor is added as another column to the grid. Let's check whether this conversion factor gives the desired unit by canceling units in the grid where appropriate. The kilogram mass units cancel. The meter length units cancel. The second squared time units also cancel. Note the second squared appear in the denominator of the conversion factor. Thus, the units also could be placed in the numerator of the factor. This is illustrated in the note box. This may help you understand why the second squared units cancel. The final quantity has a unit of Newton, and its value is calculated using the values in the grid. Engineering quantities should be expressed with the correct number of significant figures. The number of figures reflects how accurately a quantity is measured. The process to determine the number of significant figures is illustrated here. The number is calculated by finding the first non-zero digit that is furthest to the left of the value, and counting the number of digits to the right until reaching either the last digit if a decimal is present, or the last non-zero digit if a decimal is not present. For 0.000160, the first non-zero digit furthest to the left is 1, as indicated by the arrow. Now the number of digits is calculated starting with the 1 and moving right until reaching the last digit because a decimal is present. The 1 is the first significant digit. The 6 is the second significant digit. The 0 is the third significant digit. You should be able to determine the number of significant figures for each of these values. The answers are provided on the next slide. Press S to pause if you want to do the work before proceeding. Then press S again to restart. The number of significant figures are indicated in the table along with arrows indicating the first and last significant figure. Once again, press S to pause to look at this table, and then press S again to start. When performing a calculation, the number of significant figures of the result depends on the number of significant figures used in the calculation and the type of calculation. When adding or subtracting, the result first should be calculated retaining all figures in the value as illustrated. Next, determine the location of the last, furthest to the right, significant figure for each value used in the calculation. The arrows indicate the location for each value in this example. The result of the calculation should be rounded to the leftmost last significant figure of the values used in the calculation. The leftmost last significant figure is in the tens place. This is the location for the factor of 0.10. And the arrow indicates the location in the result. Rounding the result to the tens place gives a value of 3.07. This is the value that should be reported in a homework or test problem. Note that the value should be rounded up if the next digit is 6 or larger, and down if the next digit is 4 or smaller. If the next digit is a 5 and is followed by at least one non-zero digit, round up. Otherwise, you may round up or down. For example, 3.07 3.501 should be rounded to 3.08, while 3.07500 may be rounded to either 3.07 or 3.08. Rounding for a second example of addition is illustrated here. The location of the last significant figure for the factors is indicated by the arrows. The location of the leftmost last significant figure is in the tens location, as indicated in the calculated result. The result is rounded to this figure. For multiplication and division, the number of significant figures for each factor is determined. The result of the calculation is rounded to the smallest number of significant figures of the factors. The number of significant figures is indicated for both factors in the two examples here. The smallest number of significant figures is 1 in both examples, so both results are rounded to one significant figure as indicated.